This problem is about percentage uncertainty. A coin is made in the shape of a thin cylinder as shown in this picture. Here is the thickness of this coin and this is the diameter of this coin. The picture 2.2, which is this table right here, shows the measurements made in order to determine the density rho of the material used to make the coin. Calculate the density in kilos per cubic meter. Density, also represented by the Greek letter rho, is mass over volume. This table provides the mass of the coin, but we don't have the volume here, so we need to calculate. The shape of this coin is kind of really flat type of cylinder. The cross-sectional area is a circle, and the height here is the thickness. So the volume of this coin is the area, which is circular, times the thickness, which will be the height. So here we have the area in terms of the diameter is pi d squared over 4 times the thickness, that's called t. So doing the substitution, pi over 4, the diameter is 22.1 mm square times t is, now t is the thickness, is 2 mm. So notice that I'm using the units provided in this table, and I did my substitution with the units. However, my answer needs to be given in cubic meter. Now I'm going to replace m, this m right here, with 10 to the minus 3. 10 to the minus 3. This way, by doing the substitution with m with 10 to the minus 3, so I will have my result in cubic meter. I just repeat the same thing that I had here at the bottom of this table. It's the same thing, I didn't change one thing. The only reason I did this is because I was getting out of line. So here is, I'm going to resume from this formula, from this equation right here. Now I'm going to calculate this. So it will be 22.1 EE negative 3 square times 2 EE negative 3, all these divided by 4, and times pi. I'm going to try to write this in scientific notation, so the decimal should be here. So 1, 2, 3, 4, 5, 6, 7. 7 point, so V is 7.67 times 10 to the minus 7, now is cubic meter. So notice here that meter, after I did my substitution with m, which is 10 to the minus 3, this m is for meter, was square, so meter square times this meter here, so that's how I ended up with cubic meter. Okay, so now I have volume, and here is my mass. However, because my answer is in kilograms, I need to convert grams to kilograms. So I multiply this times 10 to the minus 3. So 9.6 times 10 to the minus 3 will give me kilograms. And this value is in cubic meter. So the units that is showing right here. I'm going to use my calculator. 9.6 EE negative 3 divided by 7.67 EE negative 7. So this is a pretty large number. This is 12,516.29 kilograms per cubic meter, or meter to the negative 3. It's the same thing. For the structure type of test, it would not be proper to write a number like this. The best way to do it is to round to kind of type of whole number. So in this case, we can do 12,500 kilograms per cubic meter. Now we need to calculate the percentage uncertainty in the density. So then you have to look all the variables that are involved in the formula. We have mass and volume. However, you don't have volume here, but you have the diameter and the thickness. So we need to use all this information to find the percentage uncertainty. So I label mass M, thickness T, diameter D. So here is the fractional uncertainty for those three components. Now, all that I need to do is divide the uncertainty by the value. Uncertainty by the value, and uncertainty by the value. Okay, now we have all partial uncertainties, and you have to pay attention one thing. The diameter for the formula for volume is E square. Because it's square, so the uncertainty for the diameter is double. So we need to express this right here. So it will be 2 times this fractional uncertainty for the diameter. However, the problem is asking the percentage. So you have to multiply the fractional uncertainty by 100%, every single one. So now you are going to add all percentage uncertainties for each component that make the formula for density. Okay, so 5.2% plus 0.5% plus 0.9% is 6.6%. The last part of the problem asks to state the value of density with its actual uncertainty, which means not in percentage, not fractional, which like a long decimal one, but with a unit. So now we have to add the unit to this uncertainty. So the fractional uncertainty for the density is 6.6%. So to add the unit for density, which is this one right here, all that you need to do is now multiply rho times 6.6%. Just do that. Now, you are not going to use the rounded value to present this result. You are going to use the one that you did not round. So the rho is 12,516.29 that you calculated times 6.6%. Now you have to divide it by 100. Now this is the actual uncertainty. You see, there is a unit there. So how you got this? You multiply all these and you got 826.1 kilograms per cubic meter. So that is the uncertainty for density. Because you round the value of the density, you also round the value of its uncertainty. So you do 800 should be fine. So that's the final answer. So now this is the summary of this problem. A coin with this dimension and with these values with uncertainties was given and is asking the density in a unit that is not the one that is presented here. So that is tricky because you need to convert whatever is in millimeter to meter, which is 10 to the minus 3. You just replace the m, this m, with 10 to the minus 3m. And then you calculate the value of volume, and then you calculate the value of density. You round because it's a very like long number, so not be a proper way to present the result. And then you calculate all the partial uncertainty, however, the percentage. And then you add them. Now the final one is asking that you give the actual, the density with its actual uncertainty. So then you need to add to this percentage uncertainty a unit. In order to add a unit, so you need to multiply by the value of rho and keep the original one, not the round one. And now we have the actual uncertainty of the density. And then you present your final answer as is indicated.